Let's investigate a quantum particle inside a three-dimensional rectangular box. This is a generalization of the one-dimensional particle in a box, which I covered in the previous video in the quantum mechanics playlist. Let's start off by looking at the coordinate system. I'm using three-dimensional Cartesian coordinates. So I have an x, y, and z axis. And the side lengths of the box I am actually denoting by A, B, and C respectively. So A, B, and C are associated with X, Y, and Z. That's the convention that I'm going to use in this video. The origin of the coordinate system is actually positioned at one of the corners of this rectangular box. Inside the rectangular box, the potential energy, V, is defined to be 0. So this is analogous to the one-dimensional case. Inside this region, inside the box, the potential energy function is 0. But as soon as you go outside, the potential energy jumps up to infinity. So we have infinite potential surrounding the box. So the particle cannot escape. It is trapped inside this box. So that is the key idea of the particle in a box in quantum mechanics. If you had a look at this in classical mechanics, you would see a box with a particle just bouncing around, reflecting off the edges of these surfaces. So that would be analogous to a gas molecule bouncing around in a room. But in quantum mechanics, things become much more complicated. That particle can no longer have any energy. It's no longer a continuous energy spectrum. Only discrete energies are allowed, and only certain wave functions are allowed to live inside this box. So the method that we're actually going to use to solve the time-independent Schrodinger equation, in this case, is separation of variables. So let's have a look at the scenario we have. So in red, I've written the time-independent Schrodinger equation. It's a little bit different than in the previous video. Here, everything depends on x, y, and z. We have the potential energy function over here, and we have this term which is related to the kinetic energy. So on the left-hand side, we have the result of the Hamiltonian operator acting on this eigenfunction. This is a stationary state. This is a wave function. It is an eigenfunction of the Hamiltonian operator. So what we're essentially doing with the time-independent Schrodinger equation is we're finding the allowed energy eigenvalues and the associated eigenfunctions. So you can think of these eigenfunctions as eigenvectors, if you're familiar with linear algebra, where we deal with eigenvectors and eigenvalues. So we're going to find what energy values are allowed, and we're going to find what associated eigenfunctions are present inside this box. So these are for a single particle inside the box. Let's have a look at these terms. So this kinetic energy term over here, it has a minus h bar squared on 2m. That is just a constant. But what is this? This is the Laplacian, which is also called the Laplace operator. It's a second-order differential operator. So it takes into account all of the three-dimensional second-order partial derivatives. And they're going to be acting on psi. And psi depends on x, y, and z. So we're going to get a result when we differentiate with respect to x and y and z. And we're actually going to be taking second derivatives. And all of those derivatives are going to be partial derivatives. I'll write that out in full just in a moment. What about over here? We have the potential energy function multiplying psi. This potential energy function v depends on x, y, and z. But we've actually said that this guy has to be equal to 0 when we're inside the box. And we're only concerned with what's going on inside the box. Outside the box, we know the wave function is 0. So we can actually consider this term to just be 0. So I'm going to write this guy is just equal to 0. So we'll set that equal to 0, and then this term is going to disappear. So we're just going to be left with this kinetic energy term and this term on the right-hand side with the energy multiplying the eigenfunction. So now let's find what this eigenfunction is. What is psi? How are we going to solve this? Well, we're going to use the method of separation of variables. This is a common trick in solving partial differential equations. So this is now a partial differential equation because we have partial derivatives. We have derivatives with respect to x, y, and z. In the previous video, we only had an ordinary differential equation because there was just a total derivative, and that derivative was just with respect to x. And psi only depended on x. There was only one spatial coordinate. But now, because we've jumped up to higher dimensions, we have other spatial coordinates. So we have to take partial derivatives because we need to take the other coordinates to be constants when we're differentiating. So now let's go ahead and write this out in full. So I'm going to write it underneath over here. I'm going to expand this Laplacian out, and I'm just going to write the left-hand side of the equation first. And just remember, we're ignoring this term because this potential energy function is 0 inside the box. So over here, I'm going to write minus h bar squared over 2. That is just the constant that is out the front. And I'm going to open some brackets. And this is just the kinetic energy term. First, because we're dealing in Cartesian coordinates, we're going to have a derivative with respect to x, y, and z. And all those derivatives are going to be second-order derivatives. So we're going to have a partial derivative with respect to x. You can see I'm writing this little 2 notation over here because this is a second derivative. And I'm going to have the same scenario for y and for z. So I'll write that out for y. We've got a 2 over here, and also for z. So z is over here. And I want to be very clear that these guys are lowercase x, y, and z. And these functions over here are uppercase, the uppercase x, y, and z. So this is what we're going to be doing with separation of variables. We're going to turn this psi into 3 functions. It's going to be a product of 3 functions. We're going to have x, which is a function of x, y, which is a function of y, and z, which is a function of z. So to avoid confusion, I'm going to write these functions as big capital letters to distinguish them from the variables. So this is just our little trick of separation of variables. And we can do this because we can actually make a guess. We can make a guess. We can say, what if psi can be decomposed into the product of 3 functions that only depend on 1 variable? And if we make that guess and we use that type of solution, that's actually going to get us pretty far. So this is not always true. You cannot always break up a function into the product of these smaller functions that only depend on 1 variable. But luckily for us, this technique is going to work. And this technique is going to give us the correct solution. So let's keep going with this technique. All right, so I'm going to write this. I'm going to close this bracket over here. This is the Laplacian in Cartesian coordinates. So we got all these second derivatives with respect to x, y, and z. And all of them are partial derivatives. And that's why I'm writing this little curly d, because this is a partial derivative. And now I want to act with this Laplacian operator onto psi. But I'm not going to write psi. I'm going to write psi as a product of these 3 functions. And from now on, I'm not going to write these little brackets over here because it's very clear that capital X only depends on x. That's why I've chosen this notation. And it's very clear that y depends on y and z depends on z. So now I'm going to write x, y, z. It's a product. We have 3 functions in a product, and they together, when you multiply them, form psi. So what is this going to be equal to? Well, when I apply this operator onto these guys, I'm essentially going to be taking a partial derivative with respect to x of this, and be adding that to the corresponding derivatives with respect to y and z. So let's write that out in full. We're still going to have that factor out the front. We're still going to have minus h bar squared over 2m. So I'm going to keep that there. I'm going to keep it factored out. I don't want to put it in because that's just going to complicate things. So first of all, what is this partial derivative with respect to x going to do to this product over here? Y and z have no x dependence. So y and z are going to get ignored. So we can write y and z at the front. This is y and this is z. And we're just going to have this derivative acting on x. So we're going to have the second derivative of capital X with respect to lowercase x, with respect to the variable x. So that's what we're going to get for the first term. So y and z are just treated as constants. They're not acted on because they don't have any x dependence. The only x dependence is in capital X. So that's the only one that gets differentiated. And the same pattern is going to happen in the other 2 ones. So let's have a look at what happens when we differentiate with respect to y twice. So first, x and z are going to get left alone. So we're going to have x and z. They're going to remain unchanged. And the only one that's going to get differentiated twice is y. So we're going to have the second derivative of y with respect to lowercase y. And finally, let's have a look at z. Well, z is the only one that's going to get differentiated over here. And so x and y are going to remain outside the front. So we're going to have x and y, and then we're going to have the second derivative of capital Z with respect to lowercase z. So this is a little z, and this is a big Z. I'm going to close the brackets over here. So can you see what just happened? All I've done is I've applied this Laplacian to psi, and psi is written as the product of these three functions. So when the second x derivative acts on this product, only x is going to get differentiated. Y and z are going to get ignored. When we have the y derivative, x and z get ignored. And when we have the z derivative, x and y get ignored. In every one of these combinations, it's only the associated, it's only this function that gets differentiated with its associated variable. All the other guys are treated as constants. That is why it's important to consider partial derivatives. That's why we're only considering partial derivatives here. Because if we use total derivatives, then we would run into trouble. We wouldn't get the right results. So the Laplacian operator is defined with partial derivatives here. And keep in mind, this is only in Cartesian coordinates. If we had a different geometry, if instead of a rectangle or a rectangular sort of box, we had a spherical box or a cylindrical box, we would have to use other coordinate systems because they would be far more convenient to write the Laplacian. But we're only dealing with a rectangular box in this video. So let's keep going on with this derivation. So we still have this constant over here. We have x, y, z, we have x, y, z, and we have x, y, z. And it's only getting differentiated where it needs to be. So this is the left-hand side. This is just the kinetic energy term in the Hamiltonian when it's acting on this eigenfunction. What about the right-hand side? What is the right-hand side going to look like? Well, the right-hand side is just going to be the energy value, that's E, times x, y, z. And have a look over here. We have some problems emerging in this equation. The problem is that we have all of these functions out the front. Wouldn't it be nice if we could just get rid of these functions and only have derivatives over here? Well, we can do that. If we divide by x, y, and z, we're going to get rid of x, y, and z on this side, and we're also going to get rid of all of these guys. But it is going to introduce some other complicated parts. But it's going to turn out that it's actually going to separate this into three separate equations. Hence the name separation of variables. That's the name of this technique that we're using. So I'll write that underneath. What we're going to do is we're going to divide both sides of this equation by x, y, and z. And that's going to give us, right underneath, we still have this constant of minus h bar squared on 2m. And inside the brackets, this, if we divide by x, y, z, y and z are going to cancel, but we're going to be left with 1 over x. So we're going to have 1 over x, and we're still going to have this partial derivative. So we have this second order partial derivative of capital X with respect to little x. That's the lowercase x over here. What's going to happen to this middle term? Well, x, y, z, when we divide by x, y, z, the x and the z are going to disappear, but we're going to still have a y. We're going to have to divide by y because there is no y to cancel over here. So we're going to have plus 1 over y, and then we're going to have the second partial derivative of capital Y with respect to lowercase y. And the same thing is going to happen for the z term. Here we have x and y. Those are going to cancel with x and y, but z is nowhere to be found over here. Z is getting differentiated. So we need to divide by z. We're going to have 1 over z. And we're still going to have this partial derivative of z. I'll write that over here. This is a second order partial derivative. And we have big Z in the top and little z in the bottom. I'm going to close the bracket. That is our left-hand side. And what's going to happen to the right-hand side? Well, x, y, z is going to cancel with x, y, z. So we're just going to be left with E. And that's the energy. But have a look at this. We have something that just involves x, something that just involves y, and something that just involves z. We have separated the variables into three separate terms. So we can treat this as three separate constants on the right-hand side. So I can write this as Ex plus Ey plus Ez. So that's what we have on the right-hand side. Now let's have a look at what's actually going to happen. We can consider this guy over here and pair it up with Ex. We can consider this with this multiplicative constant out the front. We can pair it up with Ey. And we can do the same with Ez. So EZ is also going to get paired up with this term over here. So let's ignore y and z for now, and we'll come back to them in a second. And let's have a look at what happens with just x. So just x, if we multiply both sides by x and we just consider this term with this constant, we just mash these x guys together, that's going to give us minus h bar squared on 2m. And because we're multiplying by x, that x is going to disappear over here. We're still going to have this second partial derivative with respect to little x. And what are we going to have on the right-hand side? Well, on the right-hand side, we're going to have ex times big X. So that's just the energy of x, and we've multiplied by x. So have a look at this. This is the same equation that we had before in the previous video, in the one-dimensional case. And we can actually rewrite this in a separate form. We can turn this into the second partial derivative of big X with respect to little x. We can write that as equal to minus, I'll move all of these constants to the right-hand side. We're going to have minus 2mex, and we're going to divide that by h bar squared. That's coming from this h bar squared over here. And that is multiplying x. So we have x over here. So you can actually think of this as kx. So we can think of this guy as minus kx squared times x. So this is analogous to the previous video. So what is this function x going to be? Well, I'll write it in green over here. So this function x is going to be a function purely of x, as we've defined above, and it's going to be equal to the eigenfunction that we got in the previous video, which is root 2 over a, that's the normalization factor, and then we're going to have sine, and inside that sine, we're going to have a value that I'm going to specify as n sub x. This is n sub x. And n sub x, I'm going to multiply by pi and divide that by a, and then we're going to have the variable x over here. So this is just the eigenfunction that we got in the previous video, but I've added a subscript x over here. And that subscript x is actually going to help us out. And what I'm actually going to do is I'm going to erase this a little bit. I'm going to add an extra subscript to this capital X. And this extra subscript is going to denote that we're just dealing in the x direction. So over here, I'm going to add n sub x. So this is the n sub x value of x. So this is just the x solution. We've only taken care of the x part. We still have to take care of y and z. And the good news is they're going to be exactly the same because of symmetry. There's no reason for them to be different. It's a rectangular box. It's Cartesian coordinates. So x, y, and z are all the same. The only difference is this a is going to turn into a b and a c. So we're going to have different lengths over here. And the thing I want you to notice is inside the sign, we have something that has a value of a, and that has units of length. So this has units of length, and this has units of length. So they're going to cancel each other, and we're just going to be left with an integer multiple of pi. So that integer multiple of pi over there, that's going to be the input to this sign. So isn't that amazing? We have the lengths that cancel, so the units are actually working out. So we have this eigenfunction. What about the energy? The energy associated with this eigenfunction, I can write that over here, is we can call this E sub nx. That is equal to nx squared, and this we got from the previous video, and we can have h bar squared over 8ma squared. So 8ma squared is in the denominator, and h is in the top. And I've chosen to write this in terms of Planck's constant and not in the reduced Planck's constant. So you can also write this in terms of h bar. And you're probably going to see that in different sources. Some sources prefer to use h bar, some prefer to use h. In the previous video, I showed that these are actually equivalent. And what I've actually added over here, I've added a subscript x, because this is just the energy associated with the x direction. And nx is the index that's also associated with the x direction. And a is the length of the box in the x direction. So we've figured out everything in the x direction. We have the eigenfunction, and we also have the allowed energy eigenvalue. So this is the eigenvalue, and this is the eigenfunction. But we don't have y and z. So y and z are analogous to this. All we have to do is substitute y and z into these indices, and we also have to change a, and we have to make it b and c. And that is the only difference over here. So what I'm going to do is I'm going to write psi over here. I'm going to write it in its most general form. So this is the most general form, and I'm going to multiply 3 copies of this. So we're going to have an analogous copy for y and z. I'll do that underneath. So I'll do that in, let's say, I'll do it in blue. Keep with our pattern of red and blue alternating. So let's do that. We have psi over here. So this is psi. And what I'm going to do is I'm going to add some subscripts that are going to denote which value of psi it is. I'm going to have nx, I'm going to put a comma, ny, and nz. So those are our 3 values that are going to determine this unique eigenfunction. And this is going to depend on x, y, and z. It depends on all 3 because this is the product of x, y, and z. Those are the capital letters that are associated with the functions. So now let's write this out. So this is going to be equal to, what is the normalization constant going to be? First, I want to write down the normalization constant. We're going to get root 2 on A from this. But we're also going to get root 2 on B and root 2 on C from y and z. So we're going to get an analogous factor from the other 2 functions as well when we multiply all 3. So in total, these guys are going to multiply together, and they're going to give 8 over a, b, c. So can you see what I did there? All I did is I multiplied 3 copies of these normalization constants. So we get 1 factor from x, 1 factor from y, and 1 factor from z. And in the denominator, you always have the associated length. So over here, you have a, b, and c. That's the product of all of those normalization constants. So this constant over here is just going to ensure that our eigenfunction is normalized. So we want the, when we take psi star times psi, and we take the integral over the entire domain, that's called the square integral, then we're actually going to get a value of 1. So that's what this constant ensures. Now, what we're going to have is we're going to have a sine term that comes from x, and we're going to have associated sine terms from y and z. So I'll write that over here. So we're going to have sine of, first we're going to write down this. We have nx times pi over a, and that's multiplying x. Then we have a sine function as well, but this is associated with y. So let's have a look at that one. We're going to have n sub y times pi, and that's going to be divided by b. So it's not a, it's b over here. And we have the variable y. And then finally, we're going to have sine of nz times pi, and that's going to be divided by c, and then we're going to have the variable z over here. So this is just the product x, y, and z. We've taken these eigenfunctions, so here we have nx, and then we've just turned this into ny and nz. So everywhere where you see an a, in the y version, it turns into a b, and in the z version, it turns into a c. And you can see the variables over here are x, y, and z. So these 3 numbers, nx, ny, and nz, are the numbers that determine this unique eigenfunction. So what is the lowest possible value you could have? Well, you could have 1 for all of these ones. So nx, ny, and nz, I'll write this out on the right-hand side over here, just to make it very clear. These guys, nx, ny, and nz, are all elements of the natural numbers. So they are 1, 2, 3, 4, and so on. So any eigenfunction that you can find is going to be determined by these 3 values. So the lowest possible value is 1, 1, 1. That's the lowest possible value you can have. So if you set these guys equal to 1, 1, and 1, that is the ground state. So the ground state is given by that combination. Now what I also want to do is I want to describe the energy. So we have the energy just in the x direction, and we have the eigenfunction just in the x direction, and we use that eigenfunction to construct the general eigenfunction. Now let's use this to construct the general energy. So this is the eigenvalue of the energy. So let's have a look. What we want to do is we want to take E and we want to add some subscripts to it. So as we have up here, I'm going to write this nx, comma ny, comma nz. So those are the 3 indices that tell us the specific energy value. And this is going to be equal to, it's going to be equal to E and x, and we're going to have to add to that E and y, and finally E and z. And so what is that going to be equal to? Well, we're going to get a factor that is shared between all of them. all of them are going to have Planck's constant squared, and all of them are going to have 8m. So I'll write that out the front. So that's what all three of these guys are going to have. We're going to have h squared over 8m. But the thing that's going to differ is this index and this length. So that's going to be the only difference. So we're going to have nx squared over a squared. That just comes from this denominator. Then we're going to have a contribution from the y energy, and that's going to be ny squared over b squared. And then finally, we're going to have nz squared over c squared. So you can see that we have a contribution from x, y, and z. And this has just come from this. So I did not write this version up here for the eigenfunction because it's very clear from this definition. We're just multiplying the three values together. We're multiplying the x version times the y version times the z version. So that's how we got all of this. And over here, we're not multiplying, we're adding. We're adding these energies together. We're adding these constants. And we get that from this definition over here. So this is the most general way of writing the allowed energy levels. So these are the energy eigenvalues, and these are the energy eigenfunctions. If you prepare the system in this state, it's going to be a stationary state. It's going to remain in that state. So these guys are all coming from the time-independent Schrodinger equation. And if you wanted to write the evolution of this, what would you do? Well, if you have a general initial condition, you would write that as a linear combination of these states. You would write it as a linear combination of the eigenfunctions, and you would find some coefficients. And then you would have a complex exponential, something of the form e to the minus I with a factor that has the energy over h bar times time, as we saw in the previous video, and that would tell you the time evolution for each of these eigenfunctions. And then that superposition of all of those guys would give you the time evolution. You'd have some kind of blobs moving around inside the box. But those blobs would be contained within this rectangular box. There wouldn't be any blobs leaking out because the potential is infinite outside the box. Let's have a look at a quick special case. So a quick special case would be if we set A equal to B equal to C. So what does that mean? That would mean that the volume, so the volume is equal to A times B times C. That's this combination we have over here. That's the volume. That would just be equal to A cubed. So that's the volume. So what we would have is a cube. This is the same as a cubic box. So I'll write that over here. We have a cubic box. And that is a special case of this rectangular box. And you can imagine taking this down a notch, taking this down to a lower dimension. If you just ignore the z part, so everywhere we have a z, just ignore that, you would have the case of a two-dimensional plane. So, and if you took that two-dimensional plane and you ignored the y part, you would go back to x, and you would just have a one-dimensional version. So this is what happens when you generalize to higher dimensions. And luckily, because we're using these Cartesian coordinates, everything is nice and simple, and we can use separation of variables in a very neat way. So I'm just going to give a quick little overview of what we covered in this video. We started with this little diagram, and this diagram gave us the information to write down the time-independent Schrodinger equation and eliminate this potential term. So we defined the potential to be 0 inside and infinite outside. And that is how we've actually defined the particle in a box. We used separation of variables to solve the time-independent Schrodinger equation, and we got solutions that only depend on x, and ones that only depend on y, and ones that only depend on z. And we used these x solutions that we got from the previous video in the one-dimensional case. So we got the allowed energy values and the allowed eigenfunctions. And then we combined them together to form the general eigenfunction. So this is the general solution to the time-independent Schrodinger equation. So actually the most general solution would be a linear combination of these guys, where you take coefficients and you take a sum of these guys. That would be the most general possible way. But this is a general way to write each of those solutions. And they're specified by 3 indices. And then finally, we had to look at the energy. We had to look at all the possible allowed energy values. And then we had to look at a special case, which is the cubic box. That's when A is equal to B is equal to C. And in that case, you can actually factor out this factor of A squared, because all of these guys are going to be A squared, so you can actually factor that out. One final thing I want to mention is degeneracies. Degeneracies are when you have different ways of getting the same energy. So there's different states that have the exact same value of energy. And you can experiment with putting different values of n over here, and you can actually find that you can get degeneracies. If you take the special case of the cubic box, where all these guys are equal, then the ground state energy is going to be 1, 1, and 1, which is going to give you 1 squared plus 1 squared plus 1 squared, and you're going to have a factor of 3. So there's going to be only one way to get 3 over 8 times h squared over m. That's the only way you can get that. But if you consider the next highest energy level, if you put 1, 1, 2, that's going to be exactly the same as 1, 2, 1 or 2, 1, 1. That's only the case in the cubic box. That's where you have those degeneracies. You might have other accidental degeneracies that emerge for other rectangular shapes. So I want you to try and play around with different values and see that you can actually get 3 different states associated with the same energy. So 3 states, but the same energy. And that is actually called degeneracy. We're going to be talking about degeneracy in later videos as well. So make sure you check out the other videos in the quantum mechanics playlist. We're going to be using these ideas again and again because these are very fundamental ideas. And we've just applied them to a simple 3-dimensional model of a particle in a box. And one final thing I want to stress is that this has real-world applications. The 1-dimensional particle in a box, you can think of that as an electron living inside a long molecule, right? That's one application. The 2-dimensional particle in a box, you can think of that as an electron trapped inside a plane, or a big planar molecule, kind of like naphthalene or even graphene. Graphene is a planar molecule. You can think of it as an electron just trapped inside there and it can't get out, but it's free to move around. So this is just a model. And then in the 3-dimensional case, you can think of that as a metal conductor and an electron just moving around inside the conductor. So all these are just models. They're not 100% accurate, but they can at least get you into quantum mechanics and at least give you some possible values for the energy and some possible predictions for how the wave function might look. So make sure to find the other videos in the quantum mechanics playlist. You can find them if you click over here.